And welcome to another theorem. Today we're going to be talking about describing a surface tangent space with a chart theorem. These are getting pretty mouthful. Now, what's the claim? Well, if S is a subset of the n-dimensional real space, and if it is a K-surface, and X is some point on the surface S, then the tangent space at point X on the surface S is a k-dimensional linear subspace. So a line in the case of one dimension, or in the two-dimensional case a plane, right, is a linear subspace of the r-dimensional real space, and if, moreover, or simply if, phi is a function mapping some subset of the k-dimensional real space into S, or onto the surface S, and if it is a k-chart, and if phi of u is x for some point u on u, or in the space capital U, then the tangent space at the point x of the on the surface S is equal to the span of the following vectors. So that's del phi over del u1 at u, all the way up to del phi del uk at u. And perhaps a picture is in order. So here's our surface S. Something like this. And here we have our point X. And then we claim that this set, which is the set of all this is the set of all tangent vectors at point X of the surface S, and I can draw this k-dimensional linear subspace that I talk about. It will be a plane passing, a plane which contains the point X, right? And we say that this is actually equal to the span of these vectors. This is the span of the, the span of all the individual partial derivatives of the k-chart phi mapping the area about X. Right, so that's an illustration, and now on to the proof. So the proof falls naturally into two parts. We shall demonstrate two facts. One, that if I take any vector from this span, it automatically lies also in the tangent space. That will be the first. And the second will be that if I take any point from the tangent span in the tangent space, it is also in the span. In other words, we shall show that there exists a bijection between the two sets. Right, and therefore we will show not bijection, we'll show set equality, which is precisely what we want. So, part one, we shall show that if V is an element of the span, this implies that V is an element of the tangent space. Alright. Well, let us have one such vector. So let V be a member, an element of this span, right? The span of the partial derivatives of phi. Of course, these are vector derivatives. And hence these are vectors, so it makes sense to talk about spans. Alright, thus V can, since it is part of the span, it can be expressed as some linear combination of these basis vectors, or of these spanning vectors. So V can be written as the sum iterating through 1 to k, which is our dimension, of some coefficient alpha I times the spanning vector. Right, and we know that... Oh, I'll also assume that V is non-zero. As it is non-zero, we know that at least one of these coefficients is non-zero, and thus we know that the vector of the coefficients is not the zero vector. Right. Now put the curve C at the point D equal to phi of u1 plus phi 1t up to uk plus alpha k times t, where t is from some small neighborhood delta, and let delta be small enough so that, well, so that what? So that this is contained in capital U. Now, it is clear that, so clearly, C is non-singular. For a curve, what it means to be non-singular? Well, it means that C is not equal to the zero vector anywhere, right? Or rather that its derivative is not equal to the zero vector anywhere, which is very easy to verify, because if I took the derivative of C, oh well, actually there's a simpler argument. Phi is a k-chart, and thus C as a subset of the k-chart is also non-singular. So there's an easier way to get to this conclusion. And clearly, C is not, well, not so clearly, but it is non-singular. And it is a non-singular parameterized curve on the surface S. Now observe by construction that C of 0 is nothing else than X. Right. Why? Because, well, if I took my time, I would say that C of 0 is phi of U, and that is X by definition. I was also mention that, and I should have done it earlier, I will also mention that U is equal to U1 through U1 to UK. Maybe should have mentioned that earlier. Right. Alright, so this is by construction. And we are nearly finished with this part of the proof. Now we only show that C prime at 0 is actually equal to the sum iterating through 1 to k of alpha I times del phi over del ui, so the partial derivatives. But this is of course V. Now, one can see this by definition. Well, simply by computing actually the derivative of C prime at 0, that be of phi at U. By simply computing this derivative, it is easy to do because it is a function of a single variable. Right, so by direct computation we arrive at this, and this by definition is equal to V from up here, which concludes the first part of the proof. Now, the second bit. This will be a bit shorter. Now, before we were showing that whenever V was in the span, it then was also part of the tangent space. Now we shall show that if V is part of the tangent space, then V is in the span of the partial derivatives. Now, alright, let, again, V be part of the tangent space. And let it be non-zero. Alright, hence, there exists a non-singular parameterized curve C, which maps some interval I onto the surface S, and there is some t0 from this interval, such that C at t0 is equal to x, and such that C prime at t0 is V. We have this by the definition of the tangent space. We have the assurance of the existence of such a curve by the definition of the tangent space. Right, now, without any loss of generality, log, let Ci be part of phi u, which is x. Right. Obviously not. Right, we know that the curve C at least passes on some interval of t0 through x, right? And we simply assume that the whole interval is mapped onto the surface, right? That we don't have like some situation like this. If it were not so, we would simply contract the interval. Right, so without any loss of generality, we can assume that already everything is fine and nothing needs fixing. But if it weren't, we would know how to fix it. Right, then, by the previous theorem, so that will be curve on a surface theorem. So by this theorem, we have that C is equal to phi after u for u equal to the inverse of phi after C, which is a map which maps some the interval I from C into space U. Okay, but and why did we bother? Well, because now if we take the partial derivative of C with respect to t at point t0, we get by the chain rule, and following some iterating through 1 to k, we always have some, well, it's just the del phi del ui at the point u t0 times ui prime at t0. But alright, but this means simply that what I mean to say is that this is precisely what we wanted, because we have some linear combination. This is just a number because we had a curve, so, well, yeah, this is just a number derivative at a point. So this is a constant, so we have a series of constants multiplying our summands, and V is equal to C prime at t0 from here, and thus we can write V as the linear combination of the partial derivatives of phi at some point, call it u, doesn't matter, which is precisely what we wanted. So yeah, this implies that V is in the span of phi del u 1 at some point call it u asterisk, doesn't matter, up to del phi del uk at u asterisk, which is precisely what we wanted.